Assalamualaikum warahmatullahi wabarakatuh, and good day to everybody. Again, this is PMM 1533 Strength of Materials 1. Actually, we are already in a new chapter, which is in CO3 with the title of Pure Bending. Well, I'm Dr. Siti Rabiatul Aisyah binti Idris, will be your lecturer for today's lecture. So hopefully you will enjoy for the rest of the class. Okay, so by today's topic, students should be able to analyze the stresses and strains problem in members subjected to pure bending and transverse loading. And the rest of the lesson objective is stated such as follows. So for today, we are going to look at on bending, stress in bending, and also strain in bending. These are the typical engineering structures which you may found out there, which includes, for example, the bridge, tables, and so on and so forth. So from these examples, can you identify the structural members subjected to bending? Yes. Yeah, okay, you are right. For example, if you look at this bridge, the part that will suffer bending is the bridge itself and the support. Other than that, for this one, part that will suffer bending is this part. And for table here, yeah, if you look at this table here, the failure part is actually the one which suffers bending. So what will happen when component or member is subjected to bending? Obviously, it will bend like this. This one showing you a members suffering a bending at both sides. This one and this one. Whereas for this one, it shows you only one end of the member suffering a bending. Okay, if you look at closely to the members that subjected to bending, so the moment here is bending being applied on the structure on the member, and the grey part here is the neutral phase, and that line is actually the neutral axis line. And for strain due to bending, the formula is strain equals to negative y over c times with strain maximum. Y is actually represent the location, the distance that we want to find the value of strain there. Divide by c. C is the distance between, from the neutral line until the maximum point of the component or member, and times with value of strain maximum at the maximum part of the members of or component. The negative and positive is actually represent the bend, the component which suffers is whether compaction or contraction, contraction or compaction. Other than that, we are going to look at on stress distribution, stress due to bending. And if you look at here, this is the neutral axis line, and this is the stress distribution happens to the components or the members when a bending being applied on the members. So by right, if you look at this diagram, the bend force is actually coming from the bottom moving to the upper part, and therefore the upper part, the parts, the upper part, this section will suffer compaction, and this one will suffer contraction. And by right, from this calculation, the formula that you need to remember for stress due to bending is sigma equals to my over I. And for the it's either negative or positive. It's actually depending on which side that we want to find the stress. For example, if we look at for this figure, if you want to find the value of stress at the upper part, then this side will suffer negative stress, whereas for the lower part will suffer positive bending. So remember, always locate your neutral axis line. From there, you will know whether it will suffer positive or negative stresses. Now, let's move on to beam section properties, because we know that beam is actually various in shape and sizes. It is not only rectangular in shape, but there are other types of shapes like W shape, S shape, H shape, and I shape, and many more. If you still remember the textbook that I recommended to you, and also the workbook, at the end of the book itself, you may find the list of different types of beams, beam properties, and also beam section. So please look at that books and also workbook. So we know that the formula for stress is sigma equals to my over I, and for beam section it represents as S, which means S equals to I over C for section modulus. So from the formula sigma equals to my over I, you can change to sigma equals to m over S. I is section moment of inertia. So a beam section with a larger section modulus will have a lower maximum stress. Does it make sense to you? It means, in other words, that if the value of S is larger, then sigma will decrease. Again, I repeat, if the value of S is larger, value of S here is larger in value, and therefore sigma will increase. So in order to get a higher strength of beam, you will need to design the beam with lower section modulus, so that it will help the components to hold a higher maximum of stress. Okay. So basically, all the information, all the formula that been introduced to you is known as flexure formula, and this is actually the summary of those flexure formula. For strain due to bending, sigma equals to my over I, with I is moment of inertia. Now to understand the lecture better, then let's do this example together. A beam has a rectangular cross section and is subjected to stress distribution as shown in figure below. Find the internal moment M at the section caused by stress distribution using flexure formula. So we know that flexure formula is sigma equals to my over I. Alright, and sigma max is given to you, which is equals to 20 megapascal. Y equals to 60 mm. Neutral axis is defined as line NA, neutral axis, because stress is 0 along this line. Since the cross-section has a rectangular shape, the moment of inertia for about NA is determined from the formula for a rectangular, which is I equals to BH3 over 12. So calculate the value of I, moment of inertia, then substitute into flexure formula, which is sigma equals to my over I. From there, substitute all the information given in the question and rearrange it back. You will get the value of M equals to 2.88 kilonewton meter. Okay, cool. Now let's move on to the next section, which is deformations in transverse cross-section. Well, in this part, the most important thing that we want to find is the radius of curvature, which is defined as the formula of 1 over rho equals to m over ei. Flexure formula, the radius of curvature is the value of rho there. It's defined as rho. So you need to rearrange the formula in order to get the value of rho here. Okay, now let's move on to another example. A cast iron machine part is acted upon by a 3 kN couple. E is given 165 gigapascal, and it says here that neglect the effects of fillet, find the maximum tensile and compressive stresses, B, the radius of curvature. So let's look at how to solve these problems. Okay, number one is we need to calculate the location of the section centroid and moment of inertia. So divide this one into two sections, section 1 and section 2. From here, if you still remember how to calculate the centroid. Alright, so taking the area for section 1, 20 times 90, and then its centroid y bar. This one is the neutral axis line, or x-axis, from point here until the center of section 1, which is 50 mm. After that, times y bar, it's y bar with area. After that, we'll find for section 2, which is the area is 40 times 30. After that, it's y bar from neutral axis line from here into its centroid, which is 20. From there, the formula for y bar is the summation of y bar times a for each section divided by summation of area for each section. From there, you will get the value of y bar, which is equals to 38 mm. So from figure here, you can locate 38 mm is from neutral axis line until exactly before section 2 there. After that, once you get the y bar, then you can calculate the value of I. If you notice here, this one is rectangular. So the formula for Ix, if you still remember, you need to refresh again this equation from static. So Ix equals to summation of I bar plus AD square. A is area, D is the distance. So I bar for a rectangular, again BH3 over 12. Alright, so you need to do it for each section. From there, you'll get the value of I, which is equals to 868 times 10 to the power of -9 m to the power of 4. From there, you can calculate the value of moment of stress due to moment. So sigma my over I. Sigma for point A. Point A is located, if you look at the question again, where is point A? Okay, the question asks you to find maximum tensile and compressive stresses. So the maximum part is the upper part of your component, which is C equals to 0.022. So this part. And for compressive stress, which is below your y bar, C equals to 0.038 meters. So substitute all the information into the formula. You'll get the value of maximum tensile stress, which is equals to 76 megapascal, and compressive stress is equal to negative 131.3 megapascal. Okay, after that, the question asks you to find radius of curvature, the value of rho there. So there must be center of curvature somewhere. Using this formula, M is already given to you, E is already given, and I use the value that have been calculated from the previous slide. So you'll get the value of rho equals to 47.7 meter. Cool? If you do understand, then please revise the question. Try to do it yourself and then compare it again with the answers given. So now let's move on to another part, saying bending is bending of members made of several materials. We know that some design, it requires to have more than one types of materials, and therefore they need to combine with different types of materials in one design. And sometimes whenever we refer to different types of materials, obviously it will have different properties, and at the same time it will suffer different stress distribution, like shown in this figure C here. So if we refer to this section as material 1 and this one material 2, the equation to the formula to transform the section is defined as N equals to E2 divided by E1. Why not? Why the equation is such as follow? Why E2 divided by E1, and why not divide E1 to E2? Well, it depends. It depends which materials that you want to transform. All right. If we want to transform the materials into materials 1, then N equals to E2 divided by E1. If we want to change the material into material 2, then E1 divided by E2. Okay, and of course the cross-sectional area will be changed. In terms of dimension, it will be changing, whereby it will become much more bigger because the original material itself has higher properties. Why do we need to change or transform this material? Well, this one is to make us easier to calculate the value of stress and to locate its neutral axis point. From there, we know how to design the materials itself. Okay. Now let's look at this example to make it more understandable. Bar is made from bonded pieces of steel. So what is steel? Steel is in the middle. E is given, yang modulus of steel is given, is equal to 200 gigapascal. Brass at the side, both sides, brass equals to 100 gigapascal. Determine the maximum stress in the steel and brass when a moment of 4.5 kilonewton meter is applied. If you refer here, steel is 200 gigapascal and brass is 100 gigapascal. If you look at here, from your own perspective, I guess, what would you change? Whether you want to change the steel to brass or brass to steel. Okay, cool. So if you refer here, by right, to make it easier, we can change steel into brass, because steel only have one part here, whereas brass have two parts. Okay, so transform the bar to an equivalent cross-section made entirely of brass. So how to change it? Firstly, you need to transform the section with the formula N equals to E steel divided by E brass, because we want to change everything into brass, so we need to divide with brass. 200 divided by 100 equals to 2. So the value of N is 2. And therefore, the cross-sectional area for steel is changing. For example, so this is the new cross-sectional area for parts which is made entirely from brass. Okay, instead of 18 mm, it become 36 mm because 18 times with 2. How about its thickness? Well, nothing changed with the thickness. Because the volume is still the same. No, the thickness, nothing changed with the thickness. It's only the width. Yeah, because the volume, we want to maintain the volume. We want to maintain its volume. After that, evaluate the transform cross-sectional properties. I, for rectangular, I equals to BH 3 BH cube divided by 12. So I equals to this value. And then calculate the maximum stress using fracture formula. Substitute all the information into the formula and you'll get the value of maximum stress equals to 85.7 megapascal. So how, if the question, okay, basically this one sigma maximum for brass. So how to find the value of sigma maximum for steel? So remember the value of N here, just times with value of maximum, and therefore 2 times 85.7 megapascal. So from there you get the value of sigma maximum for brass is 85.7 megapascal, whereas for sigma stress for a sigma maximum for steel equals to 171.4 megapascal. Well, that's it. How to calculate question design with which have different types of materials. Okay, now let's move on to reinforced concrete beams. Yeah, we know that some concrete have reinforced with steel in there, and therefore we also need to calculate its value of stresses in that concrete. Okay. Reinforced concrete beams subjected to bending moments are reinforced by steel rods normally. Yeah, the steel rods carries the entire tensile load below the neutral surface. The upper part of the concrete beam carries the compressive load. Okay, again, the upper part of the concrete beam carries the compressive load because you know that steel always expand, and therefore the upper part of the beam will carry compressive load. In the transform section, for reinforced concrete beam is slightly special. Okay, if you refer here, the cross-sectional area for the steel AS here, AS is replaced by the equivalent area N times AS, where N equals to E steel divided by E concrete, because we want to change everything into concrete, so N equals to E steel divided by E concrete. So how can we find the value of the location of neutral axis line here, because we don't know. All right, So you things that we need to do is we need to find moment at neutral axis line by assuming that this is its neutral axis line. All right. So from this equation by right, we should be able to find its exact location. Okay, so bx is area times with distance from neutral axis line, x over 2, divide NAS, this cross-sectional area, times d over x, d minus x, because this distance minus x, we'll get this distance somewhere equals to 0. Why negative here? Because it is below neutral axis line. So from there, we can get the value of x or d there. Okay, after that, using the same flexure formula, which is sigma equals to my over I. And if we want to find the value of stress in steel, sigma steel equals to N times with sigma x, or sigma in concrete. So that will be all for this lecture. Hopefully we will meet again in the next lecture by tomorrow. So see you again, and with that, thank you very much, and bye bye.